So let's start. Good evening, everyone. I am Harshit Agrawal. Welcome to the fourth live session of mine for the week 4 of the course Structural Dynamics CE07. So in today's session, we will cover following things. First, we will just review what was covered last week, that is in week 3 of this course. Then we will see what was taught in week 4, a brief overview just to brush up the content and get everyone on the same level, followed by a series of two questions, each one different from the other, based on the content covered in week 4 and assignment 4. I will first explain you the question and then step by step we will solve the question. So make sure you all have a pen and a paper besides you so that you can solve along with me. Now, in today's session, we will use MATLAB while solving the questions also, along with some initial pen paper calculations. And in these questions, I have tried to cover as much content as possible, and going through them will provide you much more clarity and confidence over the topic taught in the week 4. Finally, in addition to MATLAB used in previous two questions, that is question 1 and question 2, we will again see MATLAB coding for a couple of more cases taught in week 4. Just like the past sessions of mine, I will step by step guide you how to code in MATLAB and you will see the results. So if you have access to MATLAB, just keep it keep it open in your laptop or PC. Else just write syntax along with me and try to replicate it later on, and if any doubts can ask me in the next live session. So I hope everyone are clear with the instructions. If you have any doubts, can raise hand or write or query in the chat box. I will respond as soon as I will see. Okay, so let's start. During the week 3 of the course Structural Dynamics, we learned about undamped and damped forced vibration. What are these? These are structures under some external dynamic force, and these dynamic force are generally harmonic force without or with some damping element present in the structure. Okay, so if we talk about undamped force vibration, the solution of differential equation would be as per the following equation, where we have two types of responses: steady state response and transient response. So the first two term of the deformation versus time obtained are the steady state response, which involves natural frequency, and the final term is the transient response, which includes the forcing frequency. That is the frequency of the external force that we are applying. So with time, the transient force will die off, and only the steady state response will remain. And for damped vibration, the solution of differential equation comes as follows, where again there are two parts: steady state response part and transient response part. And the values of constant C and D are given as per the equation, and A and B depends upon the initial boundary conditions. We saw several problems related to undamped and damped force vibration in single degree of freedom system, and also wrote a MATLAB code for the same. The figure on your screen shows the result of MATLAB code that we wrote last week on how structure behaves in undamped and damped forced vibration condition. As you can see in the left figure, that is in the undamped one, due to application of force, the response is a little complex than it used to be when there was no damping. Then there was free vibration. But still, the response is uniform since there is no damping. But in the right figure, due to application of force and presence of damping, the amplitude of response decreased from initial state. And as we discussed in the last session, with time, only steady state response prevails and the transient response dies off due to damping. So here also one can see initial response is both steady state plus transient, and later on it's just steady state, and the transient one is like an envelope to the curve. Okay, so I hope these two responses from the last week were clear and how we wrote the MATLAB code for them. Now, last week, that is in week 4, we went on to learn about single degree of freedom systems with vibration induced due to arbitrary force, that is random force or non-harmonic forces. So according to the definitions, these are structures under some random external dynamic force without and with some damping element present in the structure. We also learned about Fourier transformation and what it is. So it helps us to convert an ordinary differential equation into an algebraic equation, and thus helps us to visualize how a response in time domain can be converted into frequency domain and vice versa as per convenience or need. The content in the week 4 was divided into different modules. As in week 4 module 1, we learned about the responses to arbitrary forces and a procedural way to solve them. We will discuss that quickly again so that everyone are on the same level. In module 2, we read about some special cases for arbitrary forces in which we looked at suddenly applied force, linearly increasing force, and finite time period force. And in all three, for both undamped and damped systems, we saw how the displacement profile would look like. We will visualize these cases via MATLAB in this session, and in the final module of the week, that is in module 3, we read about Fourier transformation, in which we first saw what is Fourier series and then solved the dynamic equilibrium equation via Fourier transformation. So moving ahead, just we will just brush up all the formulas and the relation we saw this week so that everyone can understand numericals and MATLAB part coming ahead properly. So just to brush up, dynamic equilibrium equation is given by inertia force plus damping force plus stiffness force is equal to externally applied force. Assuming that the frame is rigid and deflection can happen only in horizontal direction and the mass of the supporting columns are negligible, the actual frame structure can be transformed into an analytical model as shown in the figure. Now, this is something we have been reading since week 1 of this course. So this week we saw response to arbitrary forces. So what are the steps to solve dynamic equilibrium equation with arbitrary forces? First, any force can be seen as a series of impulses. What is impulse? It is nothing but a large force acting for a very small time for a finite interval. Now, at any time tau, the response of a structure to a unit impulse, that is force into time, or can be written as P of tau d tau, can be written as follows, where h of t minus tau is the response to the unit impulse. Now, a large arbitrary force is nothing but a summation of series of impulses. So, the response to all impulses can be written as the following equation. This method of finding response is also known as convolution integral or Dulomins integral. So we saw in the week content how we proceed on with these steps, and we saw, and so solving this for undamped and damped structures, we can obtain following relation. So for undamped structure, for damped system, the response can be written as U of t is equal to 1 upon m omega d whole integral of 0 to t p of tau multiplied by e to the power minus epsilon omega d t minus tau times sine omega d t minus tau d tau. And for damped system, the response can be written as omega t u of t is equal to 1 upon m omega n integral of 0 to t p of tau sine omega n t minus tau d tau. So these are the relationship that we obtained following the steps that we discussed in the previous slide. So apart from the responses to arbitrary forces, we saw Fourier transformation. So what is Fourier series? Any function, Fourier series says that any function can be expressed as a sum of series of sines and cosine and is given as following. F of t is equal to a constant term plus summation of and from 1 to infinity a constant multiplied by cos omega n t plus a constant multiplied by sine omega n t. So using this Fourier series and solving a dynamic equilibrium equation using Fourier's transform gives us a data which helps us to convert time domain function into a frequency domain function and vice versa, and thus we get the following relationship between deformation in terms of frequency as a relationship of force applied in terms of frequency. Okay, so this is what we saw in this week. Now, moving to the question part, the first question is as follows. I hope everyone are clear with what was covered in the week 4. Any doubts in the content covered in the week 4? Okay, so we will see the questions now. So, first question. The question says a one-story building shown in figure is modeled as a 4.5-meter high frame with two steel columns fixed at the base and a rigid beam supporting a total weight of 20 kilonewton. Each column has a section modulus S is equal to 25 into 10 to the power 4 meter cube, and the modulus of elasticity is given as 200 gigapascal. Determine the maximum response of the frame to a rectangular impulse. I guess this. So we need to determine the maximum response of the frame to a rectangular impulse of amplitude 10 kilonewton, and the duration Td is equal to duration of 1 second applied horizontally on the top member of the frame. The response of interest is the horizontal displacement at the top of the frame and the bending stress in the column. So it is the case of a sudden impulse that is applied for a short duration of time, and we need to find the uh, horizontal displacement at the top of the frame and the bending stress in the column. So I will give you a couple of minutes to reread the question and think how we will proceed ahead. Just think about all the steps that we used to solve in our previous session and how in this session we'll go ahead. Okay, so let's see the solution now. So what are the things given in the question? We know the height of the frame. We know the section modulus of the steel frame and the modulus of elasticity. We know the weight of the base, that is 20 kilonewton, and we know that a rectangular impulse of 10 kilometer is applied for a small duration of 1 second initially to the frame. And we need to find the displacement response and the bending stress of the columns in the columns. Okay, so the first step, as always, will be determining the system parameters. So, what are the values that we know, and what are the values that we can derive from the questions first? So, first is the stiffness coefficient of the beam. So the force is acting at the end of a fixed beam, and so what is the stiffness necessary to deflect the free end for by 1 unit? It is given by 12 EI by L cube. But since we have two columns which are in parallel, so in the week, in the first live session of mine, I have told you that when two columns are in parallel, so the equivalent stiffness is direct summation of the stiffness of both the columns. But now in our case, both the columns have the same property. The equivalent stiffness will be 2 times the stiffness of one column. So it will be 2 into 12 EI by L cube. We know the value of E, that is 20 gigapascal. So gigapascal will convert into megapascal. Megapascal is nothing but Newton per millimeter square. So it will be 12 into 200 into 10 to the power 3 into I BD cube by 12. So we know the value of width and the depth of the column 8 and 24 centimeters. So we'll convert them into millimeter. So it would be 18 into 240 cube by 12 divided by length of the column, which is given as 4.5 meter. Again we converted into millimeter. So it will be 4500 whole cube. Now, upon calculation, we will obtain a value 4.85 into 10 to the power 6 Newton per meter. Okay, so upon all the unit conversions and everything, you will obtain this value. Now, this is the stiffness coefficient. Second is natural frequency and time period that we can determine from the values given in the question. So, the natural frequency of the system, omega n, is given by under root of k by m. We know the value of k, we know the mass. Mass is nothing but 20 kilonewton, it is given. So, substituting, the weight of the frame is given 20 kilonewton. So first we need to find mass. Mass is nothing but weight upon acceleration due to gravity, which is 9.8 meter per second square. So substituting all the values, will get natural frequency as 48.75 radian per second, and thus time period is nothing but 2 pi by omega n. So 2 pi upon 48.75, so it will come out to be 0.1288 seconds. Okay, so these are some values that we can derive from the question. Now, what is the next step? Next step is to determine the maximum displacement. Now, in the weak content, we saw when a rectangular impulse is given. So, what kind of impulse is given in the question? There is this impulse that is applied for a short time, and after that time, when there is a force that has been applied for a short interval of time, and after that time, the force has been removed. So, it is according to relation P of t is some P naught for t less than a time interval td, and after that p of t is equal to 0 when time interval exceeds td. So in our case, p naught is nothing but 10 kilonewton and td is nothing but 1 seconds. So the response to an undamped system, our case is undamped system 1, that we learned that for an undamped system experiencing a rectangular impulse for a short duration, the response is given as, for time less than or equal to td, u of t is given by p naught by k times 1 minus cos omega nt. And when the time is above td, the response is given as u of td into cos omega nt plus velocity at time td upon omega n sine omega n t minus td. So these are the relationship that we derived in the session that was covered in week 4 of this module. And we know u of td is nothing but substituting t is equal to td in the first equation, that is for t less than or equal to td. Now, how to solve this question? For this, we will require the assistance of MATLAB coding. So in MATLAB, what we will do, we'll first give all the initial values will determine all the, we will feed in all the initial values that is given in the question. Then we will set a time range, and then we will calculate the response, and then we will plot the response, and from the response we will determine the maximum displacement. Okay. So I will request everyone to please open their MATLAB if they have, or write the syntax along with me. I will wait for a minute for you to open the MATLAB, and then I will start the add procedure. So this week, both the questions will involve both pen paper calculation as well as MATLAB coding, because the questions are much more complex and they can't be solved completely via formulas and everything, because it will make it very difficult to get to the solution. And by plotting the results in a coded way, we get a better understanding about how the things is happening. Okay, so let's start with the code. As usual, the first step is to define the values that are given in the question. So what are values that are given in the question, or that we derived? We derived the time period. So what value we got for the time period? We got time period is 0.1288 seconds. So time period is this value. So omega n will be nothing but 2 pi by t. So 2 pi by t. So this is natural frequency. It is given P naught, that the force that we applied is 10 kilonewton, or we can say 10 into 10 to the power 3 Newton. So 10 to the power 4, 10,000 Newton. And the value of stiffness coefficient we derived, it came out to be 4.85 into 10 to the power 6. So it will be 485. So 485 and 4 times 0. So these are the values that are given in the question, or we derived from the values present. Okay. Now, second step is to define the time related parameters. What all parameters are there in this? The observational range, for how much time we need to observe. So let's observe the response for 10 seconds. And what is the least count we can keep? Let's keep the least count of 0.001 seconds. So what this line means, after every 0.001 seconds, we will get a value, and this value will continue on till 10 seconds. So we'll get a large number of values, and then when we will plot the data, we'll get a very proper smooth curve. Okay. This is the range in which we will study. And up to what time the force was applied, P naught force, it was applied for 1 second. So TD is equal to 1 second. Now we have defined all the values. So let's go on with the estimation part. So first, we need to define all the parameters that we need for defining the equation. So first is the steady state response, UST, which is nothing but P naught by A. You can see in the workspace in the right, every value that we define is stored. Okay. Now we need to estimate the response with two functions. Why two functions? Because before TD, the response is different, and after removal of the force, the response is different. So our two functions will be for T less than or equal to TD and T greater than or equal to TD. We saw the equation for both. Okay. Now, how to define this? So for this, we'll use for loop. So what for loop will do? It will run our function for all the time, like from 0, then 0.001, then 0.002 up till 10 seconds. So why we are using for loop? Because for time less than TD, for less than 1 second, we need to use a different function which will define a deformation, and for time greater than 1 second, our function will be different which will define our deformation. So using for loop, our time value will change from 0 to 10 seconds for every time step, and then we can define the function accordingly. So how we'll define the function? We will use a if else loop. So if the time is less than or equal to td, what is the response? For time less than or equal to td, the response is given by this equation. E of t is equal to p naught by k 1 minus cos omega n t. Okay, there will be one more bracket. Okay, so we can say u of I. Why we are using I? Because I is the time parameter now, and we are storing it in the form of matrix, so that later on we can plot it. So u of I is nothing but u of t time 1 minus cos omega into ti. These use of for loop and if else loop are very basic functions in MATLAB. If you are not clear about this function, you can look it on the MATLAB official site and you will get the clarity. Or what is the pronoun? Okay, we missed one bracket, I guess. Yeah. Let me solve the problem now. U of I is equal to UST times 1 minus cos omega times P of I. There is some mistake in the code. Let me see. Let's rewrite the code once again. I don't know where the problem occurred. Okay, so first we'll define the given values. It was time is given by this, omega is given by this, p naught is this, and k value is this. Okay. Second, we need to define the time related parameters. So first is t, which is given by this, and td is 1 second. Now we'll see the estimation. So first we define the steady state deformation, which is given by P naught by K. And second is estimation with responses due to two functions. So for this, we first define the for loop. So for I is equal to 1 to length of t. If ti is less than or equal to td, P of I is equal to UST times 1 minus cos omega times. Okay, so this is the response of U of I. Now this is when time is less than 1 second. Now when time is greater than 1 second, what is the response? The response is given as a sum of two values, u of td into cos omega n t plus u dot td upon omega n sin omega n td. So this is uh, our first constant, and this is our second constant. So let's name this constant as argument 1 and this constant as argument 2. So argument 1 is nothing but u of td, which we can get from the above equation, that is p naught by k 1 minus cos omega n td. And argument 2, again we will differentiate the first equation, so it will be p naught by k omega n sin omega n td upon omega n. So omega n will cancel out, and p naught by k is a constant value that we can take out and define later on. Okay, so argument 1 is nothing but 1 minus cos omega times td into cos. Argument 1 is this whole value, okay, into cos omega and td, to cos omega into t of I. This should be t minus td. Okay, there was a mistake in my thing. Okay, so cos t of I minus td. So you need to define all the brackets properly so that there is no mistake. So this is argument 1. Argument 2 is sin omega td times sin omega t omega n td. This is the value of this, and sin omega n t minus td, sin omega t of I minus td. So this is the second argument, and u of I is nothing but ust times argument 1 plus argument 2. I hope this part of the code is clear to you. We just divided this whole equation into two arguments. This is argument 1 and this is argument 2. And since p naught by k is a common element in two argument, we took it separately outside. Okay, so it is p naught by k ust times argument 1 plus argument 2. Okay, so in this way we have defined the response, the deformation response for the using two functions for time less than 1 second and for time greater than 1 second. So we just end both the things. First we need to end the if else loop, and then we will end the for loop. So you can see in the right hand side we have got a deformation matrix of 1001 points. Okay, let's leave this error here only and let's see what is the result right now. So we will plot the response and umax estimation we will do. Sorry. So for plotting we'll use the command plot t comma u. T and u are of same length. There is some error in this code. I don't know why this error came. Let me see. Somehow there is some problem in the code part, but I have done the same thing before and I have the solution, so I will explain you through that solution right now. You can try it, the same thing again in your in through your MATLAB file, and if there is any problem in that also, you can report to me. So see in this command what we did. We first defined the given values, then the time related parameter. We did all the estimation and we plotted the response. So when you will plot the response would come out to be like this. So you can see until the force was applied, that is till 1 second, the displacement profile is little upward. And when the force is removed, the displacement profile shifts downward. Now, why this happened? Because as soon as the force is removed, the response will be under a natural vibration state. So that is why it is vibrating around Mach 0. Okay, so this is what we saw during the weak content also, like how the displacement response changes when a sudden force is applied. Now, when you will use this function u max is equal to absolute of max of u, you will get a u max value of 0.0041 second. So this is the maximum displacement, 0.0041 meter. So this is the maximum displacement value. How we can find it to a MATLAB code. Okay, now once we have determined the maximum displacement, the third step is to determine the maximum bending stress. So for determining the maximum bending stress, we have done this question previously also. First, we need to determine the maximum shear force in the column. So it is nothing but given by zero point 0.5 k u naught. U naught is the maximum displacement. So substituting all the values, we will get Vmax value is 9.494 kilonewton. Then the maximum bending moment in the columns, it will be given by mx is equal to vmax into L. Vmax we calculated in length of the column, we know 4.5 meter. So it will come out to be 44.741 kilonewton meter. And knowing the maximum bending moment, maximum dynamic stress is given by maximum bending moment upon section modulus. So the value of section modulus we know, and the value of maximum bending moment we know. So you do the unit conversion properly, so to get them in the same units, and you will get the value of 178.9 megapascal. So this is how we will solve this question. So here we first determine the deformation. We've plotted the deformation curve. Then we determine the maximum deformation value from the curve. And then we determine the maximum bending stress acting in the columns. I hope this question was clear. Sorry for that part where MATLAB code was not running somehow today. I hope this part was clear. You can try the MATLAB coding on once by yourself also, or else I will clear it in the next session. Okay, so any doubts in this question? Else we'll see the second question now. So what this question says: consider that a tower shown in figure. It is subjected to a constant impulsive acceleration of magnitude zero point 0.5 into acceleration due to gravity is applied at the foundation of the tower. So there is a constant impulsive acceleration applied at the foundation of the tower as shown in the figure by a term us. Determine the response of the tower in terms of displacement and velocity of the mass relative to the motion of the foundation. Also determine the maximum acceleration of the mass and assume damping coefficient to be 20%. So I'll give you 5 minutes to read this question and then we'll see the solution. Okay, so this is the problem. Here we missed a multiplication sign. So it doesn't consider the argument to value. So this UI function was also not defined. So that's why only 1000 points were there in the final UI function. And that's why the plot t comma u didn't was not plotted because the vector of was not of same length. So there was a multiplication sign that we missed here. So you can do that correction, and then you will when you will write the code again, you will get the response like this. Okay, so let's see the solution for this question now. So first, again, we'll determine the system parameters. So we know the stiffness coefficient, that is 100 Newton, and the mass is given as 50 Newton. So mass weight of the tower is 50 Newton. The stiffness coefficient of the column is 100 Newton per meter. Okay. So substituting both the values, what we'll get? 100 into 9.8 upon 50. Why 9.8 upon 50? Because it is given weight, not mass. So you'll get the natural frequency as 4.43 radian per second. And second is the damping factor. So we have been given damping coefficient epsilon, which is 20%. So what is the damping factor C? So for this, we will first determine the critical damping. It is nothing but CCR is given by 2m omega n. We know the value of m, we know the value of omega n. So it will come out to be 45.2 Newton second per meter. And then the damping coefficient will be given by critical damping into damping factor will be given that critical damping into damping coefficient. So it will come out to be 45.2 into zero point 0.2. It will be equal to 9.04 Newton second per meter. Okay. So these are the system parameters that we define. Now, again, we will require assistance of MATLAB for solving this problem. Why? Because it is of damped forced vibration, which is a little bit complex. A second degree ordinary differential equation is very difficult to solve on a pen and paper. So in the last session, we saw how we write a code for a damped force vibration in MATLAB. So we will first define a function. That function will yield two values. First is the velocity response and the deformation response. And then we will use an ODE 45 function of MATLAB, which helps us to solve two first order differential equations simultaneously. So we saw uh, this procedure in the last session, where we first convert that second order differential equation into two first order differential equation, and then we will see how we'll solve the thing in MATLAB. So just go through the last session of mine, so that you can get a better understanding. So UF2 is nothing but velocity, and yeah, and UF1 is nothing but displacement response. Okay, so we'll see how we'll use the displacement and the velocity response today. Okay, so let's again use the MATLAB for coding. So we'll clear this. Now first part is to define a function. Okay, so this is the general layout of a function. So what will be our first line? Function will yield a deformation response. We will name the function as it is single degree of freedom 2. Last time we named the function as 1. Now this we will yield the function as 2. And the final step will be u is equal to, we saw this syntax in the last class also. U of 2, that is the velocity response, and the displacement response is nothing but t by m minus omega square times u of 1 minus 2xi 2xi omega times u of 2. So we saw this response, how we derived this response in the last class, and here also you can see this is the second term and this is the first term. Okay, so we are determining both displacement as well as velocity. So we are solving two single order differential equation at once. and using ODE45 function. Now, what will come in the middle? We will define all these values. What is P, what is M, what is omega, everything needs to be defined here. So, first part is the given values. So, given value, mass will be 50 Newton, so 50 upon 9.8. A stiffness coefficient is given by 100. Omega will be nothing but square root of A by M. XI damping coefficient is 20%, so 0.2. Critical damping is we calculated 2m omega n, so it is 2m omega, and damping factor is nothing but CCR times XI. Okay, so these are all the values that we have defined here, and then we'll define the forcing function. Forcing function is nothing but P. So P is nothing but minus ma. So there is a constant acceleration, ground acceleration that is acting, and the value of the ground acceleration nothing but zero point 0.5 g. So P is nothing but minus ma. So minus m times 0.5 times g is nothing but 9.8. So this is our forcing function. Okay, and using this forcing function we have determined the estimation. Okay, so this is how we'll define the function. We need to save the function by the name SDF2. I earlier also defined the same function, it will just replace it. Okay, so now we have defined the function, so we will write the code now, the main body of the code, where we will call this function using ODE45 function. So again, what are the given values that we need? We need to determine the delta t, that is what is the smallest interval in which we need to record value. So let's say it is 0.01. After every 0.01 second we need a value. Okay, time span, let's go till 5 second, so it will be 0 to delta t till 5. Any doubts? Okay, I had some notification. Okay, so this is the time span for, so from 0 to 5 second we will observe the function, and after every 0.01 second we will get the value. Okay, okay, we did a mistake. It is not delta, it is delta t. Now initial condition. So initial condition, since it is not given in the question, let's assume that initially velocity and displacement both are 0. Okay, so this is how we define the initial condition. Now we need to plot the displacement response using OD45 function. So how we do that? We saw the syntax in the last class. P comma U. So the first part is the time, second part is the response, deformation response. In second part again we'll have two matrix, two columns. The first will be for velocity and the second will be for displacement. Okay, so you can see in this function u of 2 is nothing but derivation of u of 1. U of 1 is the display, this is the displacement response, and this is the velocity response. If you got the clarity in how we derived this function, you will know what output we'll receive. Okay, so ODE 45, the first part of the code is the ODE function. So that is at the rate SDOF2. The second part is the time span. So T span we define. And the third part is the initial condition, so that also we have defined. I don't know why this error today also came. Let me check. So much errors are coming today. Yeah. Okay, this is the problem. There is a semicolon here. Okay, these small index mistake, na, they create error. Okay, so now we can see there is no error. While coding, you need to be very clear with the small mistakes. Now let's define the response. So U max we need. So U max is nothing but maximum of absolute of U of dash comma 1. So you can see here U is a 500 cross 2 matrix. So the second column of this U represents the displacement and the first column represents the velocity. So that's why we have taken the second column. All the row values in the second column. So this represents all the first rows, and in the first column is of the displacement, second column is of the velocity. So all the values in the row for the first column will give us the value of deformation, and maximum of that will give us the maximum deformation value. And you will reread this code now, you will get much more better understanding. Okay, so this is how we define the umax. Second is to determine the velocity. So velocity is nothing, let's define it by u dot. It is nothing but the second column of the function. So it will be given by this, and u dot max is the maximum velocity, will be given by maximum of u dot. Okay, and third is the acceleration also we need, no? So what is acceleration? Rate of change of velocity. So u dot dot is nothing but gradient, rate of change of velocity. How we define rate of change? By gradient. So gradient of velocity function times delta t. So this is how we define rate of change of velocity. Okay, and u dot max will be the maximum acceleration. It will be given by u max of u dot dot. Okay, so in this way we have defined all the three functions. Now we need to plot the results. So we have seen this before when we need to plot multiple graphs. What we do, we create a figure first, and in this figure we'll call subplot. So since we need three plots, so we'll define 3 comma 1 comma 1. So there will be three rows and one column. And in the first row, I will define the response for displacement, which will given a t comma u dot star 1. Okay, and I will label the x-axis as time in second, and label the y-axis as displacement in mm. Okay, so this is the first response. Now we'll see the second plot, that is subplot 3 comma 1 comma 2. So the second row in 3 comma 1 matrix. So there are the figure is divided into three rows, first, second, and third, and we are now entering into the second figure. the figure has three part, we are entering the second part now. So again, now we will have t comma u comma 2. Second part of the response that we got, x label again will be time, and y label this time will be velocity. The velocity is nothing but millimeter per second. Okay, and the third part will be subplot 3 comma 1 comma 3. So again, we will plot u dot dot, that is acceleration. X axis will be again second, and y axis will be acceleration, so meter square per second. Okay, so we have defined all the three plots. Let's look at the response. Now you see in the workspace in the right, you are getting the value of maximum acceleration, maximum velocity, and maximum displacement, because we called these functions earlier on. Na? And since we use a semicolon at the end, we didn't get the value here. But the values are stored in the database. So these are the maximum responses, and how the plot is looking like. So this is the response. So you can see, due to damping present in the structure, the response is slowly dying off, and this is how the velocity, the acceleration, and the displacement will vary with time. For this system, where constant ground acceleration has been applied, and there is a a damping of 20%. Damping of 20% times the critical damping is present. Okay, I hope this response is clear and how we wrote the code. So first we defined the function. This and this are things that is always there in a function. You need to remember this, and in between define all the given values in the question which is needed in the function. And then we'll define the time periods, and then we'll call the OD45 function using the basic syntax, and then we'll plot the response. So this function has two parts. The first part is the displacement response, U of 2, and the second part is the velocity response of the function. Okay, you can see here also. Del U2 by del T is this equation. So this U of 2 is the displacement, and this is the velocity response. I hope this code was clear to you. Okay, so these are the two questions that we needed to discuss today. Now, let's move ahead. So you can see here, I have listed all the functions that we used and what is the response that we got. Okay, so now as a part of additional learning in every live session of mine, I covered a tutorial on MATLAB where we describe a single degree of freedom system. So in week 4, we have already seen couple of questions how to use MATLAB for solving the single degree of freedom system. Additionally, let's quickly see couple of more cases just to wrap up the session. So what we will do, the basic syntax of the code we have written uh, the in the previous question, the question 2, in that syntax only we'll make some changes and we'll see the responses. Okay, so first part is using values that we found in the question to plot the response with initial condition as damping is not present. So in that question we consider damping is present 20% times the critical damping. Now what if damping is not present, what will be the response look like? Okay, so what changes we need to make in the code? Can anyone tell me? We need to change this value. Xi will make 0. Okay. So when we make Xi 0, so the damping factor C will be automatically become 0. Okay. So just change the Xi value to 0 and save the code again. Okay. Save the function again. So this changes have been made. But here, what you need to do, you need to clear everything and you need to rewrite the code, so that the changes are incorporated. Okay. So I will again write the code so that it is clear again. So first are the given values. Since last time there were a couple of mistakes that we did, this time we'll again write the delta t again. Let's say delta t is 0.02 second. After every 0.02 second, we record a value. Time span, let's observe the result till say 10 seconds. Okay. And initial condition, since it is not given, let us assume that initially the system is at rest. Okay, so these are the initial conditions. Now we'll plot the displacement using OD45 function. So how we write the question, how we write the signal t comma u is nothing but ODE45. We'll call the function SDOF2 that we have defined with changes, time span that we have defined, and initial condition value that we have defined already. If there is no mistake, there it won't show any error. It is again a mistake. Okay, we wrote the wrong name. It is SDOF2. Okay, so you can see the displacement response has been recorded. So it has two parts. First part has the displacement. Second part is the velocity. Since ODE 45 function is solving two first order differential equations simultaneously. Okay, now we need to. Okay, we don't. You here you can see the displacement and the velocity response. This value how it appears. So for 501 points, that is after every 0.02 interval how the displacement and the velocity function is changing. Okay, now we'll display the response. So again, for displaying the response, display first u max is nothing but max of absolute of u of the first column defines the u max value, no? This is the umax. Now velocity u dot is nothing but the second column, na? And u dot max will be given as max of u dot. And u dot dot is acceleration. It is given by nothing but gradient of u dot dot. Nothing but gradient of velocity with time. So u of dot comma 2 comma delta t and u dot dot max the maximum acceleration at nothing but max of u dot dot. So you can see in the right hand side all the values are recorded. What is the maximum deformation, what is the maximum velocity in the response, and what is the maximum acceleration in the response. And finally we will do the plotting. So again we will create a figure. In this figure we will define subplots. So we will define three plots in this. So 3 comma 1. So with 3 comma 1 we have created three rows and in a column. So in the first row of that column we will plot the first subplot, and it will define that plot t comma deformation. So deformation nothing but 0 comma first row. Okay, X label and Y label I am leaving. You know how to define the X label. Let's define also. X label is given by time in seconds, and Y label displacement in mm. The more you will code, the more clarity you will get. Subplot 3 comma 1 comma second row of the column. So plot t comma u second row, second column of that function, is the velocity, x label again is time in seconds, and y label is velocity in per second. And finally, subplot 3 comma 1 comma 3, it is nothing but plot t comma u dot dot. So its label will be again time in seconds, and y label will be acceleration in square per second. Okay, so we have created all the three plots. Now let's look at the response. So this was the response that we got for damped structure, where the damping coefficient was 20% of critical damping. And when we remove the damping, you can see the response. So response is uniform response. Okay, so you can see how damping can affect a structure's response. So initially, all the things are varying from the same point, 0, 0, and acceleration is somewhere between -4 and -5. Here also 0, 0 and acceleration is somewhere close to -5. And then here the response is uniform, but here the response is dying off with time. So this is our response of this function. I hope you got the clarity of how damping is affecting the structure and how we can visually see it in MATLAB for all the three responses: deformation, acceleration, and velocity. Is this clear? Okay, so let's see the last part of the class. So here again you can see the response. Now we have talked about both the kinds of special cases that we talked in the session. One is when the force is suddenly applied, and the other one is when the force is there constantly there from the start. There was one more case where the force was linearly increasing. So let's see that case also once. So using the finding illustrated in question 2, plot the response with initial condition as instead of a constant force, there is a linearly increasing force. P naught is equal to zero point 0.5 times acceleration due to gravity, and this linearly increasing force is applied for 1 second, and this time we need to consider damping of 5%. Okay, so let's see how we will do the coding for this. Okay, I'm closing these two figures now. So what all changes we need to make? Xi will be 0.05. Okay, and this p function definition we need to change. So how we will define p function now? P is nothing but p naught t for t less than 1 second. So if t is less than 1, t is zero point 0.5 times d. So minus, no, it is given zero point 0.5 times, so zero point 0.5 times 9.8 into t by tr. We saw in the lectures that how we define a linearly increasing force. So it starts from 0 and it is increasing till zero point 0.5 times 9.8 into t. So it is defined by this. Tr is nothing but 1. Okay, so we are directly writing 1 here. Else, when time is more than 1, the p value is 0. This is how you define a forcing function in the a forcing function within a function. Okay, so let's save this code again. So we have corrected, we have again defined the damping coefficient, and we have again defined the p value. Now Now let's redefine this function again. Rewrite the code again. Let's clear everything. Now I will use this upward tab to just quickly write the code. So first is the given values. So let's consider delta t again as this time let's observe after every 0.05 seconds. Delta t we have time span will again define for 10 seconds. Let's observe for 30 seconds. Let's say 15 seconds is enough. And initial condition again we will take as 0, comma 0. Second part will be to plot the response. So again response will be given by OD function. And once the response has been determined, we'll display the response. So maximum deformation will be given by this. You can see the value of maximum deformation on the right hand side. Velocity function will be defined by u dot, and maximum velocity again will be defined by u dot max. Acceleration function is gradient of velocity. So gradient of velocity comma delta t, and maximum acceleration is defined by u dot dot max. Okay, and finally we'll do the plotting. So plotting. So for plotting, we'll again define a figure. In this figure, we'll create subplots. So subplot 3, comma 1, comma 1. First, you will fill the first row with the displacement response. X label time second, Y label displacement. And then second subplot will be velocity response, X label time, and Y label velocity. Finally, subplot 3, comma 1, comma 3. So it will be u dot dot, that is acceleration, x label again seconds, y label this time will be acceleration. So meter square per second. Okay. So in this way we have defined all the values. Now see what is the response. So you can see how the response is going on. So initially the response is slowly dying off, and its value is also shifting a little from the x-axis. So this is how we saw in the lecture also how the response of a linearly increasing force looks like. You can change certain parameters like change xi value or change the linearly increasing function value, and then you can rerun the code and you can see what all changes happens. So this is on your end how you want to practice. I hope this part was clear, how the response look like for a linearly increasing force in a damped single degree of freedom structure. So the same thing has been written here. This is for a smaller time interval, but in the live session I described for a larger time interval. So this was all for today's session. I will be here till 8 p.m. So if you have any doubts, you can ask. Thank you.